Hello everyone, we have finally reached our last presentation. Up till now, we have delved deeply into the construction process of the USAFA's Cadet Chapel. Through this journey, we have uncovered the challenges faced during the construction and the architectural significance of this remarkable building. With this final video, we hope you can experience and discover these aspects for yourself. We wish you a pleasant journey. This is Team 2. Let's begin the presentation. During the 1940s, amidst World War II and the Cold War, the importance of air power was emphasized. Recognizing this, President Eisenhower established the United States Air Force Academy to train Air Force officers. Construction began in 1954, and the first cadets were admitted in 1955. Now, due to the diverse religious backgrounds of the cadets, it was decided to build a chapel within the USAFA to symbolize religious freedom and provide equal worship spaces. Walter Netz, part of the renowned architectural firms Skidmore, Owings, and Merrill SOM of Chicago, was chosen to design the Cadet Chapel. The USAFA is located in the heart of Colorado, north of Colorado Springs, an ideal location for flight training. Within the USAFA, which houses many facilities such as golf courses and airfields, the Cadet Chapel was designed in the cadet area where educational facilities for students were concentrated, located in the northern part of the USAFA. The Cadet Chapel stands 45 meters high, 85 meters long, and 25 meters wide, with a total building area of 5,098 square meters. The chapel features 17 spires, each consisting of 100 identical tetrahedrons, measuring 23 meters in length and weighing about 4,500 kilo each. These spires were inspired by the ancient Japanese paper folding technique of origami, which helped to intricately manipulate the interplay of light and shadow. Now inside, the first floor houses Catholic and Jewish chapels, while the second floor is dedicated to a Protestant chapel. Each chapel is uniquely designed with its own glass placement and color schemes, creating distinct atmospheres. Now with this brief introduction, let's explore how the Cadet Chapel, a symbol of the United States Air Force and a testament to the possibilities of modernist architecture, was constructed. Firstly, we needed professional knowledge and conducted surveys about the site. The USAFA is located about 18 kilometers north of Colorado Springs and encloses 72 square kilometers of the Great Plains east of the Rampart Range, which is part of the Rocky Mountains. During the formation of the Rocky Mountains, a geological structure called Dawson Arkose was formed by the mixing of alluvial fan and fluvial deposits. And this Dawson Arkose is the predominant bedrock of the area. Furthermore, several stages of downcutting and alluviation produced gravel-covered bedrock surfaces known as mesa gravel. Similarly, pediment gravel was formed through these processes and characterized parts of the site. Now, to determine if the selected site was suitable as a foundation for heavy structures like the Cadet Chapel, we conducted 3 drilling tests. These tests aimed to understand the distribution, thickness, and physical properties of the land. Initially, we expected fewer and smaller drilling holes to be sufficient. However, each test revealed that the diameter and number of drilling holes needed to be larger and more numerous than initially anticipated. This was because the initial tests indicated a more complex subsurface structure than expected, requiring more extensive sampling to accurately assess the soil and rock conditions. Now consequently, we expanded the drilling test to obtain accurate information about Dawson Arkose, Douglas Mesa gravel, and pediment gravel. And furthermore, based on various soil tests, we confirmed that our site had an approximately 10% eastward slope. These tests also provided valuable information to determine whether the site was suitable for specific construction activities or structures. The results of these tests led to the following conclusions. Through various studies of the USAFA site, we discovered that the cadet area had a lot of moisture in the soil. Now, to build on this sloped soft ground, two types of groundwork were necessary. Thus, we first planned the design of retaining walls to prevent soil from being pushed into the construction site and to assist with leveling the land. And next, we decided on the design of deep foundations using the Caisson method, which would help build a strong foundation. Before using the Caisson method, we needed to level the site with retaining walls. If we simply piled up dirt to make the land flat, the pressure and weight could cause the ground to collapse. Therefore, we needed to install retaining walls to support the dirt and prevent it from sliding. The design process of the retaining wall follows a specific structure. Retaining walls are generally over 7 meters tall and include supports known as counterforts. These counterforts connect the stem and heel slabs, better distributing soil pressure and supporting higher loads. Before designing the retaining walls, we needed to determine the appropriate thickness and height for the walls on our site. And consequently, we conducted boring tests and triaxial tests, which revealed that we needed to install retaining walls with a height of 10 meters and a thickness of 1. We excavated the area for the retaining walls and prepared the site by establishing a strong foundation with concrete or compacted gravel. Then we poured the concrete into molds to construct the walls. And after the walls were erected, we filed and compacted the soil behind them to ensure stability. Finally, we are able to confirm that our site was level. Next, we needed to establish the foundation on the level site. The soil characteristics of the site were crucial for setting up the foundation, with the properties of Douglas Mesa gravel being the most important. This gravel easily absorbs moisture from groundwater and rainfall, making it difficult to harden and causing steel to rust. Therefore, we consider the deep open Caisson method, which is partially waterproof and suitable for areas with lots of moisture, as the most appropriate solution. An open caisson is a cylindrical concrete structure with a hole in the middle. It is placed on the soil surface and the soil is excavated from inside the caisson. As more soil is removed, the caisson gradually sinks further into the ground and more caisson structures are stacked to dig deeper. Now, before installing the caissons on this leveled land, we needed additional tests similar to the retaining walls. These tests determined how deep the caissons should be driven into the ground. We drilled 3 holes on the actual site and measured the maximum extent of deformation using weight and pressure. The test results showed that the gravel impediment could not withstand much pressure, but the Darson Arcos could handle significant pressure and became stronger as it went deeper. Thus, the caisson foundation needed to reach the depth of Dawson Arcos, which meant a depth of about 13 meters. We ensured that this foundation could support a bearing pressure of nearly 100,000 kilograms per square meter, and based on calculations, we installed 17 large steel caissons to support the cadet chapel. Now that we have prepared the land for building construction, shall we move on to the next step? After the caissons were installed, further excavation and backfilling were performed to stabilize the area. First, temporary retaining walls were installed to support the sides of the excavation and prevent soil collapse. Then backfill, which refers to the process of refilling an excavated area around the foundation, was then placed and compacted around the caisson foundations and retaining walls to provide stability and support. The backfill material consisted of a mix of sand, gravel, and excavated soil to ensure proper compaction and drainage. After backfilling, the site was graded and leveled to ensure a smooth and even surface. Grading involved reshaping the land to direct water flow away from the structure, while leveling ensured that the ground was flat and stable for construction. The next crucial step was the precise placement of rebar. essential for reinforcing a concrete base which is needed to provide a solid and stable foundation for the structure, distributing the load evenly and preventing settlement or shifting over time. This process began with workers manually laying the bottom layer of horizontal steel bars 40 mm in diameter directly on the leveled construction floor. They were spaced 70 cm apart to support the chapel's heavy load. Vertical rebars, also 40 mm in diameter, were then anchored securely into the concrete base. The ends of the vertical rebars were bent to enhance anchorage and bonding with the concrete, ensuring that the bars remain securely embedded. Additionally, a second layer of rebar was placed above the first layer to manage compressive forces and formed a robust grid pattern that evenly distributed weight and reinforced the foundation's strength and stability. Furthermore, other vertical rebars were also placed to later fix the columns securely to the ground. All these bars were tied at the joints with steel ties to prevent any movement during the concrete pour, ensuring structural integrity and following the rebar to handle tension forces effectively. Now, following the rebar installation, formwork was set up along the perimeter to contain the concrete pour. The formwork used was typically made of plywood and steel, designed to create a mold for the concrete and ensure it retains its desired shape while curing. These were carefully measured and cut to fit the dimensions of the foundation, then secured in place with nails, screws, and clamps to maintain rigidity during the pour. A 50 mm layer of concrete, known as a mud slab, was initially poured to level the floor and prevent moisture infiltration, maintaining the concrete's integrity. The mud slab was poured using concrete pumps, which allowed for precise placement and efficient handling of the concrete mix, ensuring a uniform and smooth base. After the leveling layer cured, the main concrete slab was poured in sections to control the flow and ensure precision. Vibration techniques, such as poker vibrators, were used during the pour to eliminate air pockets and ensure uniformity. Workers inserted the vibrators into the wet concrete to compact it thoroughly. This concrete base acted as an intermediary layer, transferring the building's load from the structure above to the caisson foundations below. With the foundation solidified, the construction of the columns and beams began. The columns were designed to meet the chapel's unique requirements. Given the chapel's need for large, open interior spaces without interior columns, we opted for a layout featuring 11 columns on each side, spaced 7.2 meters apart. The absence of the columns in the middle of the structure was to maintain an unobstructed open space suitable for large gatherings. Each column, prefabricated in Missouri and transported to the site, measured 60 by 60 centimeters and was hollowed to balance strength and weight. The hollow design concentrated the material on the exterior walls, providing robust structural support while reducing overall weight. These steel columns were fixed onto the drilled caissons using steel plates and anchor bolts. The plates were welded to the top of the caissons, and the columns were then bolted to these plates. Once the columns were in place, sinusoidal girders or wavy girders were placed on top. These girders, fabricated to precise specifications, were lifted into place using cranes. The girders were bolted and welded to the top of the columns at multiple points to ensure stability and strength. Following the girder installation, 22 beams, each measuring 50 by 100 centimeters, were installed on top of the girders. These beams, also prefabricated and transported to the site, were lifted into place using cranes and securely connected with bolts and welding at the junctions where they met the girders. Temporary supports and scaffolding were used during the beam installation to maintain alignment and safety. Once the skeletal frame of columns, girders, and beams was completed, the construction of the floor slabs commenced. The first floor, beginning 3 meters below ground level, was established by adding a concrete slab on the top of the ceiling formed by the beams and girders. This created a robust ground floor space. The concrete was poured in sections with formwork used to shape the sections and control the pour. This method allowed for controlled curing and prevented cracks. Rebar, also 40 millimeters in diameter, was placed within these sections to further reinforce the slab. The second floor was then constructed, featuring another concrete slab placed above the first floor ceiling. Now the interior walls of the first floor were then erected. The first floor houses two sanctuaries, one for the Catholic worship and the other for Jewish services. A dividing wall was constructed between these spaces, serving not only as a physical barrier, but also as a soundproofing element to prevent disruptions between the different services. This wall was made of a combination of concrete and drywall, with an air gap between the two materials to enhance soundproofing capabilities. The drywall was installed in panels with seams sealed and additional soundproofing materials such as acoustic insulation added between the layers. On the upper floor, the Protestant chapel, which is the largest with 900 seats, was laid out. This floor is divided into three main parts: an entrance and bathroom area near the main entrance, a 68-meter long worship space, and a 7-meter long area for the chancel at the rear. Similar to the first floor, spaces for the entrance and bathrooms were created, with a slab placed above to form a mezzanine. Now this mezzanine accommodates the large organ that plays during services and provides additional seating. At this stage, the skeletal structure of the interior building was complete.
Our cottage chapel has a distinct separation between the support methods of the roof structure and the internal structure. In such cases, separate support elements are needed to support the roof structure. These support elements are arranged in the same way as the existing rebar placement process. First, the lower rebars, bent at a 90-degree angle, are placed under the first layer of the foundation rebar, which is the bottommost layer. Then, tie bars are wrapped around to secure the position of the rebars. We had to place the rebar to properly connect the frame onto this pillar structure. However, the roof of our structure has a slanted pyramidal shape that spreads out on both sides, making vertical connections impossible. Therefore, we implemented rebar placement that connects the existing pillar with the retaining wall behind it. Through this arrangement, vertical loads are transferred to the pillar below, while horizontal loads are transferred to the retaining wall. Although other elements remained the same, one key difference was that the main rebar was placed at an angle to support the roof structure. Now, we needed to install connection joints to link the roof structure to the constructed reinforced concrete pillars. At this point, we paid close attention to the properties of the roof material, which is steel. Steel expands with temperature changes, and this small movement could significantly impact the overall structure. Vertical movements were permissible, but horizontal movements were not. Therefore, hinge supports were used at the fixed points to accommodate these movements. These hinge supports were connected to the bolted hinge joints of the existing frame. Now, let's talk about the frame that connects to these hinges. The frame comprising the roof used 6-inch rebar on the outside and 4-inch rebar on the inside. Inside the frame, ladders were installed for workers to move around. Additionally, steel brackets were installed on the 6-inch outer frame to facilitate future connections with aluminum panels. Examining the structure of the frame, the exterior consists of two sides formed by roof-held truss. The diagonal members of the truss are subjected to tension, while the vertical members are subjected to compression. This structure design distributes the load effectively, enhancing stability. These frames are manufactured in Missouri and delivered to the construction site by train and truck. During the installation process, a mobile truck crane was used to position the frames, while fine welding and joining were performed manually by workers. Let's first look at how the lower frame was installed. The lower frame was positioned using a crane, and the hinge sections were connected with bolts and nuts. However, relying solely on this hinge was insufficient because the roof structure was slanted. Due to gravity, it would have been challenging to maintain the shape as the structure would tend to rotate. Therefore, before installing the lower frame, a shoring system was first set up on the second floor slab. To ensure that shoring system could more effectively transfer the load when the frame was installed, it was positioned above the existing columns and beams. Once the structure to support the frame was in place, the frame connected to the hinges could be securely fixed in its designated position. After installing 3 lower frames on both sides, the corners and vertices of the lower frames were welded to beams to facilitate the installation of the connecting frame. Through this welded connection, the connecting frames could be welded to each horizontal beam, ensuring a secure and stable assembly. For the upper frame, 2 additional frames were welded together on site to form a triangular shape. The 2 lower vertices and the inner edge of this structure were connected in the same manner, being welded to the frame connection beams. This process was repeated, and we were finally able to complete the frame of the Cadet Chapel, showcasing its beautiful 17 spires.
Once constructing the steel frame was finished, we needed to attach exterior finish panels to each face of the tetrahedral frame. For the exterior finish of the Cadet Chapel, aluminum panels were used because they were cheap, easy to process, resistant to corrosion, and aesthetically clean. Additionally, for ease of panel processing and maintenance, we decided to divide one side of the frame into 4 parts and attach aluminum panels. The simplest method to attach the aluminum frame was to secure the aluminum to the frame with bolts, but it wasn't that simple. There were challenging points. Firstly, because aluminum has low strength, it can easily be damaged. Although it's uncommon, if a heavy stone or a large hailstone falls, the aluminum panel would tear, and to prevent this risk, instead of attaching one panel to each face, we left an air layer between and attached 2 aluminum panels to the aluminum frame. Moreover, this inner face of the steel was reinforced by creating corrugations in the panel. The outer part of the panel was wrapped in an extrusion, serving as a connection between the panel and the frame. Now let's attach these panel sets to the steel. Before mounting aluminum panel sets, it was crucial to have a proper substructure installed, since the tetrahedron existed on an inclined shape from our structure. Extrusion and support were pre-installed at the 2 edges, the outermost edge of the tetrahedral frame and their inner lower. By installing the supports and extrusion first, the exact location where the aluminum panels would be installed could be preset. This ensured that the panels were correctly aligned and installed in accordance with the design intent and ensured the basic stability of the structure. In the case of the outermost support, it is connected with the extrusion of the steel frame with bolts and nuts. The lower extrusion was also secured with welding to the steel frame. Now we need to attach an aluminum panel set to the extrusion installed this way. Here, we encountered another challenge related to the expansion of aluminum and steel. Aluminum expands about 3 times more than steel when exposed to the same heat. If the aluminum were fixed to the steel frame, and the steel expanded by 1 centimeter in the sunlight, the aluminum panel will expand by 3 centimeters, potentially causing the relatively fragile aluminum panel to break. And to solve this problem, we applied slotted support and ball joint methods. When dividing one side into 4 parts, let's look at the bottom triangular shape. First, a fixed support was applied at the vertex using bolts. One connecting part of the aluminum panel set was installed with a slotted support. This allowed the edge to expand in one direction. The opposite edge was connected to both the steel frame and the aluminum set with ball joints through a piece like this. Ball joints can be compared to a joystick on a game console. They are connected by rotating balls on both sides, allowing the angle of joint to change. This allowed this edge to expand in two axes. In the rectangular parts above, without the fixed support, one edge entirely used slotted supports and the opposite edge used ball joints to allow expansion. The panel should be placed in a way that allows expansion and contraction due to temperature changes. It was recommended to use a gap of at least 2 mm between panels. The gap will be sealed with caulking silicone during the exterior finish to ensure it is waterproof and dustproof. The remaining two upper parts were symmetrical to the part just explained, so the same method could be used to install the aluminum panels. However, the inner side of the steel frame was different from the other sides as it faces the interior of the building. Therefore, it needed a specific role, which is soundproofing. Previously, we explained the soundproofing effect of the drywall between the Catholic and Jewish worship spaces on the first floor of the inner building. Similarly, drywall was used here to protect the interior space and provide soundproofing. However, since the exterior sides were already constructed, it was impossible to work from the inside of the frame. This is why the part was hollowed out when installing the extrusion earlier. The drywall was installed in this hollow space and bolted from the outside. This process was repeatedly applied to the lower module, connection module, and upper module to complete the exterior finish. After the aluminum panel was fully installed on the steel frame, next, windows were installed on the top of the aluminum panel. The Cadet Chapel, as you know, used two types of glass to provide a comfortable and tranquil indoor atmosphere for worshippers who came to worship at religious facilities. The glass used were Daldivert and clear glass respectively. First of all, a glass frame was required before glass installation. The glass frame was manufactured and transported in accordance with the size of the aluminum panel. After the frame was fixed to the aluminum panel, the work was carried out in the order that stainless glass was installed in turn, and finally, the center trapezoidal transparent glass was installed. For all construction work, the glass frame and glass were placed on the edge through manual lifting equipment and cranes. The raised frame was secured to the aluminum panel with steel clips, brackets, and bolts. As you can see in this photo, Daldivert is installed on the parts that contact the aluminum panel, and transparent glass was installed in the central trapezoidal shape. The glass frame was designed as double glazing to consider noise reduction and insulation. The central trapezoidal shaped glass consisted of double glazing made up of two transparent glass panes. Unlike the central part, the glass on the left and right sides were designed with transparent glass on the exterior and Daldivert on the interior. The following photo shows the interior after completion. Now, glass has not only been used on the sides of the chapel, but also on the north and south facades. Here, you can see that the interior wall is made of transparent glass. We call this a curtain wall. A curtain wall is a glass wall that supports only its own weight and does not bear the weight of the roof. Because of this, it can be made from lightweight material. Aluminum was used for the frame due to its strength, lightweight, and corrosion resistance, ensuring the durability and aesthetic quality of the chapel. Due to the high ceiling height and lack of slabs in the Cadet Chapel, a frame is needed to support and then secure the curtain wall. However, a shoring system is necessary to install this frame. The shoring system consists of 4 levels and was installed to facilitate workers' tasks by lifting the frame with a manual lifting beam. Once the shoring system is fully constructed, the next step was to install the frame for the curtain wall. The curtain wall frame was divided into 3 main levels. As the manual lifting equipment raised the frame one level at a time, workers simultaneously worked on the shoring system. The front glass frame, like the sides, utilized a double frame with 2 transparent glass panes. Now the final step was the installation of the curtain wall. The glass was carefully fitted into the pre-constructed frame and installed. We have now explored the entire construction process of the Cadet Chapel, from design and foundational work to the actual building. There were unexpected complexities as well as simpler aspects than we had thought. Thank you for following along with our study process.